So let's look at some simple applications of antiderivatives. A robot has been programmed so that when it starts to move, its velocity after t seconds will be 2t squared feet every second. And the first question is, how far is the robot going to travel during its first 4 seconds of movement? Well, velocity is the rate of change of position. And remember that the antiderivative of velocity will be the distance traveled, or technically the displacement, but everything's positive here, so it won't be a difference. So the distance traveled, or the displacement, just going to be the integral within the first 4 seconds, that's from the 0th second up to the 4th second, of its velocity, 2t squared, with respect to t. All right, and in general, displacement is always going to be the integral of velocity. Because of fundamental theorem of calculus in 3.1, we said the integral of a rate of change, and velocity is just the rate at which your position's changing. The integral of a rate of change is the total change. Total change is how far the robot traveled. That's why this all works. And at this point, now it's just like last section. Take the antiderivative, evaluate it between 0 and 4. We add an exponent, and we divide by that exponent. We plug in 4, 2 times 4 cubed over 3. We plug in 0, 2 times 0 cubed over 3. I like this one. This second parenthesis is just 0. Over here, 4, 16, 64 times 2 is 128. We get 128 over 3, which is like 42, approximately. 42.6 repeating. What are our units? Well, it's displacement, so it should be a distance. So in this case, it'll be feet. Another way that you can look at units is remember that the units of an integral are always the units of y times the units of x. In this case, what's the units of y? Sorry, let's not say y. Say integrand. Units of our rate, which was feet per second, times our input is actually t here. Our input is time in seconds. That's another way that you can see that our answer is in feet. Letter B says, how far will the robot travel during its next 4 seconds? Well, it's accelerating with a parabola as its velocity. So we should expect it to go much further in the next 4 seconds. Really speeding up. So the first 4 was from 0 to 4. The second 4 is going to be from 4 to 8. Same velocity function, 2t squared. Same antiderivative, 2t cubed over 3. But now we're not going from 0 to 4, we're going from 4 to 8. So very similar, 2 times 8 cubed over 3 minus 2 times 4 cubed over 3. And it's our lucky day because we already know that the second thing is 42.6 repeating. We already calculated that. The first one, I don't want to do this in my head. 2 times 8 cubed over 3. And then we're subtracting that first one. We're going to get the total displacement is 298.6 feet. I guess I did leave a space for that. We should fill that in. 341.3. So yeah, I said it's accelerating. I say it's going to go much farther in the next 4 seconds. Yeah, it's like 300 feet. In 4 seconds, this robot's really moving. That's a whole football field. And again, remember, you can check your answer. The integral from 4 to 8 of 2t squared dt. Same answer that we got. That was example 6. Apparently, I did not give you an example 7, so we're in example 8 now, which is kind of cool. I don't know how much you'll like it, but I like example 8. It connects to some other things. We have a little bit of a surprise here. A company determines their marginal cost for production in dollars per item with a marginal cost function, MC of x. It's 4 divided by the square root of x plus 2 when you're producing x thousand items. Find the cost of increasing production from 4,000 items to 5,000 items using 2 different methods. So remember that marginal cost, the definition of marginal cost is that marginal cost is the cost of the next item at your current level of production. So the marginal cost of 4 gives you the cost of the next item. But here's a little weird in this problem. Because x is in thousands of items, so it's actually going to give us the extra cost of the next 1,000 items. So when it says find the cost of increasing production from 4,000 items to 5,000 items, that is literally just the marginal cost at 4. Okay, that's the idea. That's the extra cost, the cost of the next 1,000 items, because our units are in thousands. And that's kind of our old method, how we used to do this problem. Marginal cost of 4, well, you just plug in 4 and you're done. That's 4 over 2. 2 plus 2 is 4. And that's in dollars per item. Now, this is not quite what we were asked, though. Wait, this is actually a little weirder than I thought it was going to be. So this is not the method that you're supposed to use here, but I wanted to connect the concepts. Find the cost of increasing production. Marginal cost gives you the cost. I guess this really is dollars per item. I guess we do have to multiply this by 1,000. Interesting. It's going to be $4,000 because it's 4. Oh, wow. I really can't write very well today. But here's the connection that we wanted with this problem. This not so important. Here's what I wanted you to say. Remember that the marginal cost is the derivative of the cost function. So the integral of the marginal cost with respect to x is the total change of cost. Remember way back when we introduced the idea of marginal cost, I said there's 2 definitions of marginal cost. This was one definition, and this was our second definition for marginal cost. And now it's come full circle. Marginal cost is the derivative. We can just evaluate it using this marginal cost function. Or if we really integrate it, that's going to give us the other version of marginal cost, another way of evaluating this total change in cost. What's the cost of increasing production from 4,000 items to 5,000 items? Well, the cost of 5,000 items minus the cost of 4,000 items. So this is kind of a silly problem, but it's cool because it shows how the 2 definitions we've been working with apply with derivatives and integrals, which is fun. But the second method is what the book wants you to do. So this is the integral from 4 to 5 of our marginal cost function. Let's rewrite our marginal cost function. Dividing, so square root of x is x to the 1/2 power. And when you're dividing by x, that's like x to a negative exponent. So you can rewrite it this way. Now we need to find the antiderivative and then just plug in 4 and 5 and take the difference. So we're going to add an exponent. When we add 1 to negative 1/2, we get positive 1/2. Now we need to divide by 1/2. Dividing by 1/2 is multiplying by 2. The next part of the antiderivative is much easier. The antiderivative of a constant is just 2 times, or is that constant times a variable. Remember back, again, we're using all of these formulas. We just use the power rule and then the antiderivative of a constant. And again, normally we have a plus c here, but we don't need the plus c because that's really only for indefinite integrals, and we're doing definite integrals, so the plus c will always cancel out. So we just don't write it. So our antiderivative is 8 square root of x plus 2 times x. Let's evaluate that at 4 and 5 and take the difference. 8 times the square root of 5, I'm going to put this in parentheses, plus 2 times 5 is 10. Minus 8 times the square root of 4 plus 2 times 4 is 8. Can't really simplify the first half, but we could simplify the last half. Again, this is 8 square root of 5 plus 10. Square root of 4 is 2. This is 16 plus 8. This is 24. And we could simplify and say 8 square root of 5 minus 14. Hopefully that approximates to something close to 4. So let's look. 8 square root of 5 minus 14. There it is. About 3.889. Or a total of $3,000. 889. Again, I think this problem is written a little bit odd. The cost of increasing production from this many items to this many items has got to be in the thousands of dollars. It's not going to cost $4 extra to do an extra 1,000 items. I feel like I'm missing something small in this problem, but that's the idea. So again, you can see that 2 ways of thinking about marginal cost are going to give you very similar answers. And yes, I know the integral way is way longer, but it's just practice applying some of these concepts right here. Okay. But yeah, this is the definition of marginal cost up here. Kind of a weird example because the units are a little strange, but this is the idea, and it should be some good practice to think about marginal cost as a derivative. The antiderivative of a rate of change is the total change, that sort of stuff. Let me know if you have questions, and we got one more video with more homework problems for you next.